Imagine holding a speck of dust that has traveled farther than any human could ever journey across billions of years, through the silent emptiness between stars, carrying within it secrets from the very dawn of the universe. This isn't a scene from science fiction. It's the breathtaking reality of cosmic dust, nature's own time capsules, so small they're often invisible to the naked eye, yet so profound they may hold the memory of creation itself. Each of these microscopic particles tells a story of stellar explosions, of ancient chemistry, of the raw ingredients that eventually gave rise to everything we know, the planets, the stars, even life. And what's truly astonishing is that this dust is all around us, falling gently onto Earth every day, connecting each of us, right here, right now, to the grandest narrative of all, the story of our cosmic origins. In this video, we're setting out on a journey unlike any other. We'll explore how these tiny interstellar archives preserve clues not just about where we came from, but how the universe itself took shape. We'll see how scientists are learning to read these messages etched into dust messages that have survived supernova, wandered through nebulas, and drifted for eons before arriving in laboratories here on Earth. This isn't just astronomy, it's detective work on a cosmic scale, and what we're uncovering could reshape our understanding of existence, from the formation of the first stars to the possibility of life beyond our world. So get ready, we're about to dive into one of the most captivating mysteries in modern science, a mystery written in particles smaller than grains of sand, yet vast enough to contain the history of everything. This is a journey through space and time, and it all begins with something as humble and as extraordinary as dust. But what exactly is this cosmic dust we're talking about? Think of the tiniest speck of sand you can possibly imagine. Now, imagine something even smaller, often just a fraction of that size. These are the individual particles that make up cosmic dust, drifting in the immense void between stars. They aren't all the same, far from it. Their compositions are as varied as their origins. Some are made of silicates, not entirely unlike the minerals that make up rocks here on Earth. Others are rich in carbon, forming graphite or even more complex organic compounds. And in the colder reaches of space, you'll find grains coated in a shell of water ice or frozen gases. The incredible thing is where these particles come from. They are born from both chaos and serenity in the cosmos. Some are forged in the unimaginably violent final moments of a massive star's life, a supernova explosion that blasts newly created elements out into the galaxy. Others have a much more gentle origin, condensing slowly in the cooler, extended atmospheres of aging red giant stars, which shed their outer layers like a cosmic sigh over millions of years. So each mote of dust carries with it the signature of its birth, a tiny artifact from a specific event in the life of a star. And while each one is physically minuscule, their collective role is absolutely enormous. They are the fundamental building blocks of everything larger in the universe. When a new star forms, this dust is there, swirling in the protoplanetary disk, clumping together to eventually form asteroids, comets, and entire planets. Without cosmic dust, our own Earth and we ourselves simply would not exist. But beyond just being construction material, they act as tiny, resilient canvases. As they travel for millions or even billions of years across galactic distances, they don't change all that much. They are bombarded by radiation and subject to extreme temperatures, but their core structures and chemical compositions remain, recording the conditions they were exposed to along the way. This makes every single grain a messenger, a messenger that has crossed the light years, carrying encrypted data about its birthplace, its age, and the environments it has drifted through. They are the universe's own ancient scrolls, written in a language of atoms and isotopes, just waiting for us to learn how to read them. So where does this incredible material actually come from? The origins of cosmic dust are as dramatic and varied as the universe itself, born from both celestial violence and serene, slow-motion stellar evolution. One of the most powerful sources is the supernova, the cataclysmic death of a massive star. In its final moments, a star explodes with such unimaginable force that it hurls its newly forged elements, everything from the carbon in our bodies to the iron in our blood, out into the void at nearly the speed of light. In the turbulent, superheated aftermath of this explosion, atoms rapidly collide and condense, forming the first tiny seeds of dust, which are then scattered like cosmic confetti across entire galaxies. Each of these particles carries a distinct chemical fingerprint, a specific mix of isotopes that acts like a birth certificate, pointing directly back to the fiery furnace that created it. But not all stellar dust factories are so explosive. In beautiful contrast, consider the red giant star, an aging sun in the final chapters of its life. These stars don't go out with a bang, but with a much more gentle exhale. Over millions of years, they slowly puff their outer layers out into space, creating a vast, glowing cocoon of gas and dust around themselves. In these cooler, more stable regions, atoms have the time and conditions to gently bump into one another and stick, gradually building up intricate dust grains layer by layer. This process is more like frost slowly forming on a window pane than the violent chaos of a supernova, yet it is equally important in seeding the galaxy with raw materials. And the story doesn't end there. Other cosmic phenomena add their own unique contributions to this interstellar reservoir. Planetary nebulae, the intricate, glowing shells of gas ejected by sun-like stars, are prolific dust producers. Even the protoplanetary disks swirling around young stars, the very cradles of planet formation, are sites where dust is both created and destroyed, constantly being recycled in the process of building new worlds. This incredible diversity of origins means that a single handful of interstellar dust, if we could ever collect one, would contain a library of different stories. One grain might be a rugged survivor from a long-ago supernova, while its neighbor could be a delicate, carbon-rich flake formed in the cool wind of a red giant. Each particle is a time capsule from a specific event, a specific place, and a specific time. Some are ancient, dating back to before our own sun was born, while others might be relative newcomers from a recent stellar death in our galactic neighborhood. Together, they form a fragmented but breathtakingly valuable record of cosmic evolution, a historical archive written not on paper, but in atoms. By learning to read these microscopic messages, we are piecing together the grand story of how our galaxy transformed from a primordial cloud of simple elements into the complex, dusty, and planet-filled cosmos we see today. What makes these tiny particles so extraordinary isn't just where they come from, but their incredible ability to endure. Imagine setting a message adrift in a bottle, hoping it might survive a journey across thousands of miles of ocean, tossed by waves and storms for centuries. Now amplify that to a cosmic scale. A single grain of cosmic dust is like that bottle, but its voyage isn't across an ocean. It's across the unimaginable vastness of interstellar space, a journey that can last for billions of years. These particles are the ultimate survivors, forged in extreme conditions and then cast adrift into an environment that is mostly empty, but still filled with potential hazards like radiation, shock waves from nearby stellar explosions, and the gentle but persistent pressure of starlight itself. Despite these challenges, their core essence remains locked in time. Their resilience is what transforms them from simple debris into priceless time capsules. Inside each microscopic grain, the atomic architecture remains largely untouched. The precise ratios of different isotopes, atoms of the same element that have different numbers of neutrons, stay frozen, preserving a direct chemical record of the specific star that created them. Their molecular structures, the very way atoms are bonded together, can also remain intact, telling us about the temperature and pressure of their birthplace. Some of the most exciting grains might even harbor complex organic compounds, the kind of carbon-based molecules that are the fundamental building blocks of life. This means we could be holding not just a piece of a star, but a potential ingredient for biology that formed in the dark, cold clouds of deep space long before our own planet even existed. This archival quality is what allows scientists to perform a kind of cosmic time travel. By carefully extracting and analyzing these grains in the lab, researchers can effectively peer back into epochs that are otherwise completely inaccessible. We are looking at a time before our solar system had even begun to coalesce from a cloud of gas and dust. These particles are literal samples of that primordial soup, the original mixture of elements from which our Sun, our Earth, and every one of us eventually formed. They provide ground truth data about the composition of our galactic neighborhood billions of years ago, offering clues about how many stars had lived and died to enrich the mixture, what kinds of stars they were, and how frequently they exploded. This turns abstract theoretical models of cosmic evolution into something tangible we can hold, measure, and understand. Each grain is a unique, irreplaceable piece of evidence in the grand investigation of our own origins, a silent witness to the events of cosmic creation. So how do we actually go about catching these tiny pieces of other worlds? It's a task of almost unimaginable difficulty, a cosmic fishing expedition where the quarry is smaller than a grain of pollen and traveling at incredible speeds. Scientists have had to become incredibly creative, developing a whole arsenal of methods to snag these particles without destroying them or contaminating them with the dust of our own world. One of the most straightforward approaches happens right here in Earth's atmosphere. Specially designed high-altitude aircraft like NASA U-2, a civilian version of the famous U-2 spy plane, soar into the stratosphere with collectors mounted on their wings. These collectors are essentially ultra-pure, silicone oil-coated plates that act like flypaper for tiny particles. At that altitude, above most of Earth's weather and pollution, they can sweep up interplanetary dust grains that have gently floated down from space. It's a delicate process, but it provides a steady, if tiny, supply of fresh extraterrestrial material for labs around the world. But to get the most pristine samples, the ones completely untouched by Earth's environment, we have to go much further out. This is where satellite-based collection comes into play. Spacecraft can be placed in orbit with collectors designed to capture dust in the pure vacuum of space. Some early experiments, like those on the Long-Duration Exposure Facility, simply exposed panels of materials to space for years to see what would stick. The real game-changer, however, was the dedicated sample return mission. NASA's Stardust mission was a masterpiece of this approach. It wasn't just a passive observer, it was an active hunter. The spacecraft was equipped with a collector filled with a substance called aerogel, an incredibly light and porous material that is 99.8% air. Think of it as a kind of solid smoke. Stardust flew through the coma, the cloud of gas and dust surrounding Comet Wild 2, at over 21,000 kilometers per hour. At those mind-boggling speeds, even a tiny particle could cause catastrophic damage if it hit a solid surface. But the aerogel was the perfect solution. It allowed the particles to gently burrow into the material, slowing down over a distance of centimeters and coming to a stop virtually intact. After this incredible encounter, the spacecraft stored the precious samples in a return capsule that parachuted back to Earth in 2006, delivering pieces of a comet for scientists to study firsthand. And the hunt doesn't stop at comets. Recent missions have targeted asteroids, the other great reservoirs of primordial solar system material. Japan's Hayabusa and Hayabusa 2 missions performed breathtaking feats of precision, touching down on asteroids Itokawa and Ryugu to collect tiny grains of dust and rock. NASA OSIRIS-REx mission did the same at asteroid Bennu, gathering a substantial sample that is now being meticulously analyzed back on Earth. These asteroids are like time capsules themselves, having remained largely unchanged for billions of years, and the dust on their surfaces is a direct record of the earliest days of our planetary system. Every one of these collection methods, from the high-flying planes to the intrepid deep space robots, shares one absolutely critical requirement: obsessive cleanliness. The entire process is designed around avoiding contamination at all costs. Every tool is meticulously cleaned, every handling step is done in sterile clean rooms, and every container is sealed against Earth's environment. A single fingerprint, a single speck of earthly dust, could completely ruin a sample, introducing modern elements that would obscure the ancient cosmic signature scientists are desperate to find. It's this painstaking attention to detail that transforms a speck of dust into a reliable page from the universe's history book, bringing us one deliberate, careful step closer to understanding our own celestial ancestry. But the journey of a cosmic dust grain is far from over once it's safely inside a laboratory. In fact, that's when the real magic begins. These precious, microscopic specks are subjected to a suite of some of the most advanced analytical instruments ever devised, each tool designed to tease out a different piece of the story locked within their atomic structure. It's a process that feels almost like an archaeological dig, but on an unimaginably small scale, where scientists are carefully brushing away eons of time to reveal the secrets buried inside. One of the first and most crucial tools is the electron microscope. Imagine trying to read the fine print on a coin from a mile away. That's the level of difficulty we're talking about when trying to see the surface details of a dust grain. An ordinary light microscope simply can't provide the resolution needed, but an electron microscope uses a focused beam of electrons instead of light, allowing researchers to see these particles in stunning nanoscale detail. They can map the grain's topography, examine its crystal structure, and even identify tiny inclusions of other minerals trapped inside, like finding a smaller, older Russian doll hidden within. This initial visual inspection is vital. It tells scientists what they're working with and helps them decide exactly where to aim the next, even more powerful instruments. To truly read the chemical story, researchers turn to techniques like secondary ion mass spectrometry, or SIMS. This remarkable instrument works by firing a beam of charged particles, called ions, at the surface of the dust grain. This beam acts like a microscopic sandblaster, knocking individual atoms and molecules off the sample. These ejected particles are then ionized and shot into a mass spectrometer, which acts as a cosmic sorting hat. It separates these ions by their mass and charge, allowing for an exquisitely precise measurement of the sample's elemental and isotopic composition. It's this isotopic analysis that is truly transformative. Isotopes are different forms of the same element that have varying numbers of neutrons in their atomic nuclei. The ratios of these isotopes are like a chemical fingerprint. An overabundance of a specific oxygen isotope, for example, can instantly tell a scientist that this particular grain must have formed in the heart of a specific type of supernova, because only that particular stellar environment could have produced that exact isotopic signature. For the most detailed look at how the atoms are actually arranged and bonded together, scientists might use a synchrotron. This isn't a tabletop instrument. It's a massive, stadium-sized facility that generates incredibly intense, focused beams of X-rays. By shining this brilliant light on a dust grain, researchers can perform a kind of high-energy fingerprinting. The way the X-rays scatter and are absorbed reveals the precise mineralogy of the grain and the chemical bonds holding it together. It can distinguish between different types of carbon, for instance, revealing whether the atoms are arranged as graphite, as diamond, or in more complex organic structures. This tells us not just what the grain is made of, but the conditions it experienced, whether it was formed in a hot, violent environment or a cold, gentle one. Each of these techniques peels back another layer of the story, transforming an anonymous speck under a lens into a rich narrative. The combination of data reveals the grain's age, pinpointing when its parent star died. It uncovers the extreme temperatures and pressures it endured during formation. It can even show evidence of later alteration, perhaps from a shock wave of a nearby star explosion or gentle heating from a young star. This isn't just analysis, it's translation. Scientists are learning to read the language of atoms, translating isotopic ratios and molecular structures into a coherent history of birth, journey, and survival. Each grain, once just a silent traveler in the void, becomes a readable page, and with every page decoded, we add another sentence to the grand, unfolding story of our cosmic origins. This is where the investigation turns into a true forensic science, moving from simply identifying what a dust grain is made of to unraveling the profound story of its origin. The real magic lies in the isotopes. To understand why, picture every element on the periodic table, like oxygen or silicon. While we often think of them as single, uniform entities, many actually come in different versions called isotopes. These isotopes are atoms of the same element that have identical numbers of protons, giving them their chemical identity, but different numbers of neutrons in their nucleus. This tiny difference in mass might seem insignificant, but in the cosmic arena, it changes everything. It's a fundamental signature of the specific nuclear fusion processes that created them. The mix of isotopes found in material from Earth, the Moon, or Mars is remarkably uniform, all averaging out to a standard solar system recipe. But when scientists analyze pristine cosmic dust, they often find something astonishingly different. Wild, dramatic excesses or deficits of specific isotopes that completely defy that standard mixture. These are the isotopic anomalies, and they are the ultimate smoking gun. Take a grain rich in an isotope of oxygen known as oxygen-16. On Earth, this is the most common form, but in some stardust, the amount is so extraordinarily high that it simply cannot be explained by any chemical or geological process that happened within our solar system. The only possible explanation is that this grain formed directly from the gaseous ejecta of a specific type of stellar explosion. Similarly, grains showing a huge overabundance of silicon-28 or specific isotopes of neon or nitrogen act as direct physical proof of nucleosynthesis, the incredible process where stars act as elemental forges, crushing lighter atoms together under immense heat and pressure to create newer, heavier ones. Each type of star is a specialized factory. A massive star ending its life in a supernova produces a very different set of isotopes compared to a slower burning red giant star. It's like finding a distinct manufacturer's stamp on a component. The isotopic signature is that stamp, indelibly linking the dust grain to its stellar birthplace. So the process becomes one of cosmic matchmaking. Astrophysicists spend decades developing sophisticated theoretical models that predict the exact cocktail of isotopes that should be produced in the heart of a particular star during a specific phase of its life. Then, cosmochemists in the lab meticulously measure the isotopes in their tiny captured dust grains. When the data from the model and the measurement align, it's a moment of pure discovery. They can point to a single grain under their microscope and say with confidence, "You were born in the fiery death of a Type II supernova," or "You condensed in the stellar wind of a low-mass star like our Sun, but billions of years before it existed." This isn't just theoretical astronomy anymore, it's direct evidence. We are holding pieces of other stars. This ability to trace the lineage of dust back to its source revolutionizes our understanding of our own galactic heritage. It reveals how the elements essential for life, the carbon in our cells, the oxygen we breathe, the iron in our blood, were not just created in some abstract, distant past, but were literally forged in the hearts of ancient stars and then seeded across the galaxy by these dust grains. They are the delivery system for the building blocks of planets and life. By reading these isotopic clues, we are effectively writing a new history of our galaxy, one based not on distant observation alone, but on physical samples that have journeyed across space and time to tell us their story. Each anomalous grain is a courier, delivering a message about how the universe manufactures complexity, and ultimately, how it creates the conditions for us to be here to study it. Now, let's talk about something truly mind-bending: the idea that some of this cosmic dust isn't just old, but actually predates our entire solar system. These are the pre-solar grains, the ultimate ancient relics of the cosmos. Imagine a tiny mineral particle that formed around a star that isn't our Sun, in a stellar system that vanished billions of years before our own Sun even ignited. These grains are not just messengers, they are literal time travelers, and their very existence is one of the most astounding discoveries in modern science. Their story begins not in the cloud that birthed our solar system, but in the final acts of other, earlier stars. When those stars died, whether in the gentle winds of red giants or the violent explosions of supernova, they spewed their newly forged elements into the galaxy. In those expanding clouds of gas and dust, some of the atoms managed to clump together and form solid grains. These grains then began an epic journey across interstellar space, drifting for millions, sometimes billions of years. Eventually, a vast cloud of this material, enriched by countless stellar generations, began to collapse under its own gravity. That cloud became our solar nebula, the nursery for our Sun and all the planets. And mixed into that primordial soup were these resilient pre-solar grains, tiny hitchhikers from distant stars that were literally incorporated into the building blocks of our solar system. The miracle is that they survived this entire process. Think about the violence of the early solar system, the chaotic collisions, the intense heat near the forming Sun, the gravitational turbulence that eventually built the planets. It's astounding that any of these delicate ancient grains could make it through that unscathed. Yet some did. They were preserved inside larger, tougher bodies like primitive asteroids and comets, which acted as protective vaults, shielding them from the worst of the chaos for over 4.5 billion years. It's only when these larger bodies are broken apart, or when we collect dust directly from space, that we can finally free these primordial time capsules and study them. Finding them is like finding a needle in a galaxy-sized haystack. Even in a meteorite rich in pre-solar material, they might make up only a few hundred parts per million of the sample. Scientists identify them by their extreme isotopic anomalies, the same fingerprints we discussed earlier. The isotopic ratios in these grains are so wildly different from anything that formed in our solar system that they stand out immediately. A grain with a huge excess of carbon-13, for example, or a specific isotope of silicon, is a dead giveaway that it originated elsewhere, carrying the unmistakable signature of its parent star. And that's where their true value lies. Each type of pre-solar grain acts as a direct sample of a specific kind of star. Silicon carbide grains, for instance, are thought to come mainly from asymptotic giant branch stars, a late stage in the life of Sun-like stars. Grains rich in certain isotopes of oxygen and aluminum are almost exclusively forged in the hearts of massive stars that die as supernova. By collecting and analyzing these different grains, we are effectively conducting a census of the stars that were contributing material to our galactic neighborhood just before the Sun was born. We can answer questions we could only guess at before. What types of stars were most common? How many supernovae went off nearby? What was the overall chemical makeup of the galaxy in this region billions of years ago? This provides absolutely critical benchmarks for our models of stellar evolution and galactic chemical enrichment. For decades, astrophysicists have developed complex computer simulations to understand how stars live and die and how galaxies evolve their chemical composition over time. But those models were based on observations of distant stars and theoretical physics. Now, with pre-solar grains, we have physical evidence. We can test those models against real data. We can hold a piece of a red giant star in a lab and say, "Our model predicted a star like you would produce this exact mix of isotopes," and either confirm our theories or force us to go back to the drawing board. It's ground-truthing the history of our galaxy. Ultimately, that's the profound wonder of these pre-solar grains. They are more than just scientific curiosities. They are tangible pieces of our cosmic ancestry. We are all made of stardust, but these grains are that phrase made manifest. They are unaltered, pristine pieces of other suns, preserved across the eons to tell us the story of what came before us. They remind us that our solar system is not an isolated island, but part of a vast, interconnected galactic ecosystem, built from the ashes of generations of stars that lived and died long before we ever looked up at the night sky. Now, let's take this idea of cosmic messages one step further, into a realm that touches on the very essence of our own existence. We've seen how dust carries the history of stars, but what if it also carried the very seeds of life itself? This isn't just speculation. It's a finding that has fundamentally reshaped our understanding of biology's cosmic context. Tucked away within these tiny interstellar particles, scientists have discovered a stunning array of complex organic molecules. We're talking about the fundamental architecture of life: amino acids, which are the building blocks of proteins, and hydrocarbons, the long chains of carbon and hydrogen that form the backbone of countless biological compounds. Finding these intricate structures in the void of space is like stumbling upon a fully formed sentence in a language you thought was only capable of producing random syllables. It suggests a universe that is not just physically fertile, but chemically prepped for the possibility of life. So how do these delicate, complex molecules form in an environment that is, by any human standard, utterly hostile? The vacuum of space is incredibly cold, often just a few degrees above absolute zero, and it's bathed in harsh radiation. It seems like the last place you'd expect complex chemistry to thrive. But here's the fascinating twist. The surface of a cosmic dust grain provides the perfect laboratory. Picture a tiny, cold mineral speck drifting through a vast, diffuse cloud of gas. Individual atoms and simple molecules like carbon monoxide or water slowly bump into this grain and stick to its frigid surface. They can't react with each other on their own. They simply don't have the energy. But then a catalyst arrives, a jolt of energy from a passing cosmic ray, a high-energy particle screaming across the galaxy, or a photon of ultraviolet radiation from a nearby star slams into the grain. This sudden input of energy acts like a microscopic chef, providing the heat and agitation needed for those dormant atoms to start linking up. It's a process known as surface-mediated chemistry, where the dust grain isn't just a passive platform but an active participant, its structure helping to orient the molecules in just the right way to form new, more complex bonds. Over millions of years, this slow, persistent process can build molecules of surprising complexity, right there on the frozen surface of a speck of dust in the dark. The profound implication of this discovery is that the basic ingredients for life are not a rare or unique anomaly confined to planets. They appear to be a natural and widespread product of cosmic chemistry. These organic-laden dust grains are everywhere, woven into the fabric of interstellar clouds and nascent planetary systems. This leads us to a breathtaking possibility, one that connects the cosmic to the terrestrial in the most intimate way imaginable. Billions of years ago, when our solar system was young, Earth was a violent, molten world, constantly bombarded by asteroids and comets. These incoming bodies were themselves rich in cosmic dust that had been incorporated during their formation. With every impact, these celestial delivery trucks were showering the early Earth with a rain of organic material. They weren't just bringing water and minerals, they were delivering a pre-made toolkit of life's building blocks. The amino acids, the sugars, the hydrocarbons that had formed on dust grains in deep space were now splashing into the warm, watery pools of our primordial planet. This doesn't mean that life itself arrived from space fully formed. That's a separate concept known as panspermia. Instead, think of it as a cosmic head start. The universe had already done a significant portion of the complex chemical work required for life to emerge. Instead of having to build these intricate molecules from scratch using only the simple gases of Earth's early atmosphere, the first biological systems on our planet had a rich supply of pre-formed organic compounds readily available. It's the difference between trying to bake a cake by first inventing flour, sugar, and baking powder, versus walking into a well-stocked kitchen where all the ingredients are already laid out on the counter. This cosmic delivery service could have drastically accelerated the genesis of biology on Earth, making the emergence of life not just a lucky accident on one special planet, but a much more probable event, a natural next step in a universe that seems predisposed to creating complexity. The dust that carries the memory of dead stars, therefore, might also have been the courier that delivered the promise of new beginnings, directly linking our most ancient celestial history to the vibrant biology that now covers our world. But the journey of cosmic dust doesn't end with its formation in the hearts of dying stars or its role as a carrier of life's ingredients. To truly appreciate its cosmic significance, we need to follow it into the vibrant, chaotic nurseries where new worlds are born, the protoplanetary disks that swirl around infant stars. This is where dust transforms from a passive wanderer into the active, fundamental building block of planets. Imagine a vast, spinning platter of gas and dust, a cosmic whirlpool centered on a newborn star. In the beginning, this disk is filled with nothing but fine, microscopic dust grains, all the material that will eventually become asteroids, comets, and entire planets. The process starts gently, almost imperceptibly. These tiny particles, buffeted by the gas in the disk, begin to bump into one another. Static electricity and weak molecular forces, like the van der Waals force, make them stick together on contact. It's a slow-motion snowball fight happening across millions of miles, with microscopic specks of silicates and ices gently colliding and clumping into larger and larger fluffy aggregates. This is the first critical step in planet building, the formation of what scientists call planetesimals. These are the kilometer-sized or larger planetary precursors, the mountain-sized chunks of rock and ice that are massive enough for their own gravity to start taking over. But the path from dust to planetesimal is not a straightforward one. The composition of the original dust is absolutely paramount. A disk rich in carbon-based dust and organic molecules will eventually form very different planetesimals compared to a disk dominated by pure silicate or iron-rich grains. Furthermore, the temperature gradient within the disk acts as a cosmic sorting mechanism. Close to the hot, young star, only dust with high melting points metals and rocky silicates can survive without vaporizing. This is why the inner solar system gave us the terrestrial, rocky planets like Earth and Mars. Farther out, beyond what's known as the frost line, temperatures are cold enough for volatile ices, water, ammonia, methane to freeze onto the dust grains. This allows for the formation of much larger, icy planetesimals, which is why the outer solar system is dominated by gas giants with icy moons and a vast reservoir of cometary material in the Kuiper belt. The distribution of different dust types throughout the disk, therefore, directly dictates the architecture of the entire planetary system that will emerge. It determines not just the location and size of planets, but also their potential for habitability. A planet forming in a region enriched with water ice-coated dust grains, for instance, has a far greater chance of acquiring the vast oceans that are essential for life as we know it. The dust doesn't just build the planet, it also delivers the very volatiles and organics that can make that planet a living world. This is why astronomers today are so intensely focused on studying these protoplanetary disks around other stars with powerful instruments like the Atacama Large Millimeter Array and the James Webb Space Telescope. They aren't just looking at pretty pictures, they are forensic scientists analyzing a crime scene, the scene of our own solar system's creation, billions of years ago. By measuring the composition, size, and distribution of dust in these distant disks, they can see the different phases of planet formation play out in real time. They can observe gaps and rings in the dust, likely carved by unseen, newly formed planets sweeping up material in their orbits. They can detect the chemical fingerprints of water, carbon monoxide, and complex organics in the dust itself. Each observation is a data point that helps refine our models of how our own solar system came to be. It allows us to run the experiment of planetary formation over and over again across the galaxy to see which outcomes are common and which are rare. Are solar systems like ours, with rocky worlds interior to gas giants, the standard? Or are we an outlier? The answers are written in the dust, and we are finally learning how to read them, connecting the microscopic journey of a single grain to the grand, emerging architecture of worlds. To truly grasp the grand story written in dust, we need to understand its home, the vast, seemingly empty expanses between the stars known as the interstellar medium. Though we often picture space as a perfect vacuum, it's actually filled with a sparse but crucial mixture of gas and, of course, dust. This isn't a static repository. It's a dynamic, ever-changing ecosystem where matter continuously cycles through phases of creation and destruction. Cosmic dust is not just a passenger in this system. It's an active and influential player, fundamentally shaping the life cycle of the galaxy itself. One of its most vital roles is acting as a cosmic coolant, a key ingredient in the recipe for star formation. Enormous clouds of molecular gas, the potential nurseries for new stars, are often too warm and turbulent to collapse under their own gravity. The atoms within them simply bounce around with too much energy. This is where dust grains come in. Their solid surfaces provide a place for energetic gas atoms to collide and lose that energy, effectively radiating heat away into space. As the cloud cools, the inward pull of gravity can finally overcome the outward pressure, causing the cloud to fragment and condense into dense cores. Inside these cores, the temperature and pressure skyrocket, eventually sparking the nuclear fusion that ignites a brand new star. Without dust to facilitate this crucial cooling process, the birth of stars would be far more difficult, and the galaxy would be a much darker and emptier place. But the life of a dust grain is perilous. The very stars it helps create ultimately become the agents of its destruction. When those massive, short-lived stars reach the end of their lives and explode as supernova, they unleash unimaginably powerful shockwaves that rip through the interstellar medium. These waves travel at hypersonic speeds, and any dust grain caught in their path is likely to be vaporized by the immense heat and force, shattered back into its individual atoms. Similarly, the fierce stellar winds blowing from massive stars can sandblast away nearby dust clouds, eroding them over time. It's a dramatic and violent end, a complete demolition of the grain's intricate structure. Yet, this destruction is not an end, but merely a turn in the cycle. The atoms liberated by a supernova shockwave or a stellar wind are now raw material once again, mixed with new elements forged in the stellar explosion. They are scattered back into the interstellar medium, where they will eventually cool and encounter other atoms. In the quieter, denser regions of a new molecular cloud, these atoms will once again find their way onto the surface of a surviving dust grain or begin the process of nucleating an entirely new one. Over millions of years, they will recondense, building a new particle with a new crystalline structure, ready to begin the cycle all over again. This constant process of birth, death, and rebirth means that a single dust grain we study today might be a composite artifact of unimaginable age and history. It could contain a core of material that survived the destruction of its original form, an inner structure that dates back to a stellar event billions of years ago. Layered around that ancient core might be newer material that condensed in a later stellar outflow, a more recent chapter in the grain's long life. Each particle becomes a palimpsest, a cosmic document that has been written upon, erased, and rewritten multiple times throughout the history of the galaxy. Its isotopic signatures are not from a single event, but are a blended record of every environment it has ever passed through. Deciphering this integrated history is the ultimate challenge for scientists, as it requires untangling multiple overlapping stories from a single microscopic speck. This complex recycling is what makes cosmic dust such a rich, though incredibly difficult to read, archive of galactic evolution, chronicling not just a single moment of creation, but the ongoing, dynamic life story of the Milky Way. So how do we actually see and study something as tiny and seemingly insignificant as a speck of dust from thousands of light years away? We don't look for the dust itself. We watch how it manipulates the one thing that can travel those immense distances, light. The interaction between cosmic dust and starlight is a delicate dance, a form of silent communication that allows these tiny particles to reveal their deepest secrets to anyone who knows how to listen. It's a fundamental tool of astronomy, turning an obscuring veil into a detailed map and a rich source of data. The most straightforward interaction is simple absorption. Dust grains are incredibly efficient at blocking light, particularly shorter, bluer wavelengths. This is why we often can't see the brilliant blue-white light of hot, young stars embedded within a cosmic nursery. The surrounding dust absorbs that blue light, letting only the longer, redder wavelengths pass through. This phenomenon, called interstellar reddening, is exactly why the sun appears so deeply red at sunset. The same dust in our own atmosphere scatters the blue light, leaving the stunning reds and oranges to reach our eyes. On a cosmic scale, this tells astronomers that there must be a significant amount of dust along our line of sight to that star, and by measuring exactly how much the starlight has been reddened, they can actually estimate the total quantity of dust in the way. But dust doesn't just absorb light, it also scatters it. Think of a car's headlights cutting through a thick fog. The water droplets in the fog don't absorb the light. They catch it and toss it in every direction, creating a diffuse glow that surrounds the light source itself. In space, this same process creates some of the most beautiful objects in the heavens, reflection nebulae. These are vast clouds of gas and dust that are not hot enough to glow on their own like an emission nebula. Instead, they are illuminated by the light of nearby stars, their dust grains scattering the starlight to create an ethereal, often bluish, glow. The iconic blue haze surrounding the Pleiades star cluster is a perfect example. It's not the star's light, but the starlight being scattered by a chance cloud of dust the cluster is passing through. The fact that the scattered light is blue is another crucial clue, as smaller dust particles are much more efficient at scattering blue light, giving astronomers a direct way to gauge the typical size of the grains within that nebula. Perhaps the most subtle and sophisticated interaction is polarization. Normally, light waves from a star vibrate in all possible directions perpendicular to their path. But when this light encounters dust grains that are not spherical, imagine tiny, elongated specks, perhaps rich in graphite or iron, something fascinating happens. These needle-like grains tend to align themselves with the galaxy's magnetic fields, all pointing in the same direction like countless microscopic compass needles. As starlight passes through this organized field of dust, the grains preferentially absorb the light waves, vibrating in one direction while allowing the others to pass. This process, called dichroic absorption, leaves the transmitted light polarized, meaning its waves are now predominantly vibrating in a single plane. By measuring the direction and degree of this polarization from a distant star, astronomers can actually map the magnetic field lines of our galaxy. They are using dust as a tool to trace the invisible magnetic architecture that weaves through the cosmos, an architecture that plays a critical role in shaping gas clouds and guiding the process of star formation. This isn't just limited to starlight from within our galaxy. The most profound example of dust manipulating light comes from the very edge of the observable universe, the cosmic microwave background, or CMB. This is the faint afterglow of the Big Bang, a snapshot of the universe when it was just 380,000 years old. While this ancient light has been traveling for over 13 billion years, it hasn't had a completely unimpeded journey. On its way to our telescopes, it passed through immense clouds of dust within our own Milky Way and other galaxies. This dust imprints its own signature on the primordial light, subtly polarizing it. For cosmologists trying to read the faint whispers of the Big Bang itself, this galactic dust is a source of contamination, a foreground noise that must be meticulously identified and subtracted. But for a galactic astronomer, that same signal is a treasure trove. The polarization patterns caused by this local dust provide an incredibly detailed map of its distribution and alignment throughout the galaxy, informing models of its composition and how it interacts with magnetic fields. It's a remarkable crossover where the study of the largest scales in the universe is utterly dependent on understanding the smallest. By combining all these techniques, measuring reddening, analyzing the glow of reflection nebulae, and mapping polarization, astronomers can construct stunningly detailed three-dimensional charts of the dust clouds throughout our Milky Way. They can infer not just where the dust is, but what it's likely made of, how big the particles are, how cold or warm they are, and how they are oriented by magnetic forces. Each interaction with light is a sentence in a story, and by listening to all of them, we can read the entire narrative of the dust's journey and its role in the ongoing evolution of the galactic ecosystem. While we often picture meteorites as homogeneous chunks of rock or metal from space, many are actually far more complex. They are cosmic sedimentary rocks, layered archives that captured and preserved materials from the earliest days of our solar system. Tucked safely within the matrices of certain primitive meteorites, particularly a class known as carbonaceous chondrites, are countless microscopic grains of genuine stardust. These aren't particles that formed within the meteorite itself. They are older, far older. They are individual grains of cosmic dust that were drifting through the solar nebula over 4.5 billion years ago, which gently settled onto the surface of growing asteroids, the parent bodies of these meteorites, and were then sealed inside for eons. The asteroid acted as a perfect time capsule, a protective vault that shielded these delicate grains from the ravages of solar radiation, violent collisions, and the extreme geological processing that would later reshape planets. This means that when a meteorite carrying these grains lands on Earth and we crack it open in a lab, we are not just studying a rock from an asteroid. We are handling a preserved sample of the very dust cloud that gave birth to our entire planetary system. The process of finding and extracting these grains is a monumental feat of scientific patience and precision. Researchers begin by carefully crushing a small piece of the meteorite and then treating it with a series of strong acids. This might seem counterintuitive, using harsh chemicals on something so precious, but it's a necessary step. The acids are designed to dissolve away the majority of the meteorite's material, which formed within our solar system and has a uniform, well-mixed isotopic composition. The pre-solar grains, with their wildly anomalous isotopes, are incredibly resilient. They remain behind, a tiny residue of stardust that can then be painstakingly gathered and prepared for individual analysis under those powerful microscopes and mass spectrometers. It's like panning for gold on an atomic scale, washing away tons of earthly rock to find a few precious nuggets that fell from the stars themselves. What these meteoritic stardust grains reveal is nothing short of a history of galactic neighborhood relations before our sun was born. Their diverse isotopic signatures tell us that the solar nebula was not a homogeneous soup. It was a fantastic mixture of material from a wide variety of different stellar sources. In a single meteorite sample, scientists can find grains that originated in red giant stars, others forged in supernova, and some that may even come from more exotic stellar objects like asymptotic giant branch stars. This is concrete evidence that as our solar system was forming, it was accreting dust that had been manufactured in many different stellar factories across the galaxy at different times and then delivered to our corner of space. It paints a picture of a vibrant and well-connected galactic environment where the death of one star seeds the nursery of the next generation. The fact that our own solar system incorporated this diversity is a key reason for its rich chemical complexity, which ultimately provided the varied raw materials necessary for a planet like Earth to become habitable. Furthermore, by studying the types and abundances of these preserved grains, cosmochemists can infer the physical conditions within the solar nebula itself. The preservation of certain delicate mineral types tells us that temperatures in the outer regions of the nebula where these asteroids formed must have remained relatively cool. If it had been too hot, these grains would have been vaporized or their isotopic signatures scrambled. The sheer number of grains that survived also gives us clues about the density of the dust cloud and how quickly material was accreted onto growing bodies. This provides a critical ground truth link between the world of interstellar dust, which we observe remotely in distant nebulae, and the finished products of planetary formation that we can hold in our hands. These tiny inclusions bridge a gap in our understanding, showing us the direct pathway from diffuse stardust drifting between the stars to the solid, complex worlds that orbit our sun and countless others. Yet for all the incredible promise these microscopic archives hold, actually unlocking their secrets is a task fraught with immense difficulty. The path from collecting a speck of dust to understanding its cosmic biography is littered with daunting challenges that push the very limits of modern science. The first and perhaps most persistent enemy is contamination. We live on a planet that is itself incredibly dusty, and every speck of terrestrial dust, from skin cells shed by a researcher to a fiber from clothing or a mote of pollution from the air, is a potential source of catastrophic error. A single fingerprint, rich in organic compounds and modern elements, could completely overwhelm the delicate isotopic signature of a grain that has traveled for billions of years. This is why the entire process, from collection to analysis, must occur in the most stringent clean room environments on Earth. Scientists don what are essentially space suits, working in rooms with air filtration systems thousands of times more effective than a hospital operating room, all to ensure that the only history they are reading is the one from the stars, not from their own laboratory. Then there is the sheer, almost absurd smallness of the samples themselves. We are not talking about pebbles or even sand grains. A typical pre-solar grain might be only a few micrometers across. That's smaller than a single human red blood cell. Manipulating something so tiny requires tools that are themselves extraordinary. Scientists use microscopic needles tipped with a fragment of a diamond or a human hair, all controlled by precision joysticks under high-powered microscopes. Simply moving a grain from one place to another without losing it is a nerve-wracking task that can take hours of painstaking effort. And once it's in place, the act of analyzing it can sometimes destroy the sample entirely. Techniques like secondary ion mass spectrometry essentially vaporize tiny bits of the grain to learn its composition. There is no room for error. You essentially get one chance to ask your questions before the evidence is gone forever. This forces researchers to be incredibly strategic, often using non-destructive techniques to map a grain first before committing to more invasive but more informative methods. But perhaps the most intellectually demanding challenge lies not in the handling but in the interpretation. Imagine you are a detective and you have a single, blurry fingerprint from a crime scene. Now imagine that fingerprint could have been left by one of 100 different suspects, all with slightly different motives and methods. That is the complexity of interpreting isotopic data from a stardust grain. A particular pattern of oxygen isotopes might point toward a supernova, but the specific type and size of the star that exploded, the exact conditions in the shockwave where the grain condensed, and any later processing it might have endured all leave their own subtle marks on that signature. Untangling this single, blended signal into a coherent story requires incredibly sophisticated computer models that simulate stellar physics and dust formation. Researchers must run countless simulations comparing their results to the lab data to find the best possible fit and therefore the most likely origin story for that grain. It is a meticulous process of elimination and inference where a single anomalous data point can force a re-evaluation of entire theoretical frameworks. Each grain is a unique puzzle, and solving it requires a blend of cutting-edge experimental skill and deep theoretical insight, all dedicated to reading the autobiography of a speck of dust. And this incredible life cycle of dust, from its creation in stellar furnaces to its role as a galactic coolant, is not just a local phenomenon. It's a process that scales up to shape the very evolution of entire galaxies. We often picture galaxies as vast collections of stars, but they are equally vast collections of dust and gas, and the interplay between these components dictates a galaxy's destiny, its appearance, and its ability to foster new generations of stars. The presence and distribution of cosmic dust is a primary driver in this grand cosmic narrative, influencing some of the most fundamental processes across millions of light years. One of the most direct ways dust shapes a galaxy's future is by directly boosting its star formation rate. Inside a typical galaxy, enormous clouds of molecular gas are the raw material for new stars. But these clouds are constantly bombarded by intense radiation from existing hot, young stars. This radiation has a disruptive effect, heating the gas and preventing it from collapsing under its own gravity. This is where dust acts as a cosmic sunshield. Dust grains are incredibly effective at absorbing this harsh ultraviolet and optical radiation. They effectively cocoon the densest, coldest cores of these molecular clouds, protecting them from the disruptive energy that would otherwise tear them apart. By providing this crucial shade, the dust allows the gas to remain cool and dense enough for gravity to finally win, triggering the collapse that leads to the birth of new stellar systems. This is why we often observe that the dustiest galaxies, those immense swirling structures seen in the early universe known as starburst galaxies, are also the most prolific star factories. They are literally shrouded in the protective dust that enables such frantic rates of creation, sometimes forming thousands of times more stars per year than our own Milky Way. Beyond just shielding gas, dust also actively participates in the chemical enrichment of a galaxy, a process that evolves over billions of years. As we've seen, dust grains themselves are forged from heavy elements created in stars. When a galaxy is young, it contains primarily hydrogen and helium from the Big Bang with very little dust. The first generations of stars, massive and short-lived, quickly explode as supernova, seeding the galactic environment with the first sprinkling of heavy elements and the first generation of dust grains. This newly available dust then makes the next cycle of star formation more efficient, and those subsequent generations of stars will form from gas that is already slightly enriched. Each stellar life cycle further pollutes the galaxy with more complex elements and more dust. Over cosmic time, a galaxy literally dusts itself, building up its metallicity, the abundance of elements heavier than hydrogen and helium. This increasing dust content fundamentally changes the physics within the galaxy. It makes future star formation more efficient. It alters the way light escapes and thus changes the galaxy's appearance, and it provides the material for the formation of rocky planets. A galaxy's dust content is therefore a direct measure of its age and maturity. An old, evolved galaxy like our Milky Way is far dustier and more chemically complex than a primordial galaxy observed in the early universe. Astronomers can now trace this incredible evolutionary story by comparing the dust content across different galaxy types and at different distances, which equates to different ages in the universe. By pointing telescopes like the Hubble Space Telescope and the Atacama Large Millimeter Array at incredibly distant, high redshift galaxies, they are effectively looking back in time, observing galaxies when they were young and still assembling themselves. They often find these early galaxies to be surprisingly dusty, indicating that the first generations of stars must have formed and died in a cosmological blink of an eye, rapidly polluting the pristine environment. In contrast, looking at older, nearer galaxies like our own reveals a complex ecosystem where dust is woven into the spiral arms, having been recycled through multiple generations of stars. By meticulously cataloging the amount, composition, and distribution of dust across these different epochs, astronomers are piecing together a dynamic timeline of galactic growth. They can see how the small-scale physics of a single dust grain shielding a tiny gas cloud integrates upward to influence the large-scale dynamics of an entire galaxy, how quickly it forms stars, how its structure evolves, and how it eventually may slow its own growth by locking away its raw materials in dust grains that are too cool to form new stars. This profound connection between the microscopic and the galactic underscores a central truth of cosmology. The grandest structures in the universe are intimately governed by the smallest of particles. While we've made astounding progress by studying the precious few specks of dust we've managed to collect so far, we are truly standing on the precipice of a new golden age of discovery. The next decade promises a revolutionary leap in our ability to study these cosmic archives, thanks to a suite of upcoming missions and technologies that will allow us to see further, analyze more precisely, and bring back even more pristine samples than ever before. At the forefront of this new era is the James Webb Space Telescope, an instrument that is already changing the game. Unlike telescopes that primarily observe visible light, Webb is designed to see the universe in infrared light. This is absolutely crucial for dust research because while dust blocks our view in visible light, it actually glows brightly in the infrared. Webb's incredibly sensitive instruments can peer directly into the hearts of dense, dusty stellar nurseries and protoplanetary disks, analyzing the chemical composition of that dust from mind-boggling distances. It can identify the specific infrared fingerprints of silicates, carbon-based compounds, and even ices coating the grains in disks around other stars, giving us a direct read on the raw materials available for planet formation in other solar systems, and by extension, a clearer window into our own past. But the revolution doesn't stop with remote observation. The next logical and incredibly exciting step is to go and get more. Building on the stunning success of missions like OSIRIS-REx and Hayabusa 2, space agencies are already planning a new generation of sample return missions that are even more ambitious. Imagine a mission designed not just to briefly touch an asteroid, but to carefully select and retrieve a core sample from deep within a pristine, carbon-rich body, one that has been shielded from solar radiation for billions of years, preserving the most delicate organic molecules and the most ancient pre-solar grains in perfect condition. There is even serious discussion of a dedicated mission to fly through the plume of an active comet, capturing not just dust, but also ices that vaporize immediately upon exposure to space, materials we have never been able to study directly in our labs. The technological hurdles are immense, requiring autonomous navigation, sophisticated robotic sampling arms, and even more secure return capsules to ensure these priceless samples are delivered to Earth without a single molecule of contamination. The scientific payoff, however, would be immeasurable, providing a diverse library of cosmic dust from known sources that would keep researchers busy for decades. Perhaps the most profound future application lies in the study of exoplanets. We are rapidly moving from simply discovering planets around other stars to actually characterizing their atmospheres. The next generation of giant ground-based telescopes, like the Extremely Large Telescope, and future space observatories will have the power to analyze the light filtering through the atmospheres of distant, Earth-like worlds. And what will they be looking for? The telltale spectral signatures of dust. Not just any dust, but the specific kinds of silicate or carbonaceous dust that could only be suspended in an atmosphere through persistent volcanic activity, massive dust storms, or even industrial pollution. The presence, type, and quantity of atmospheric dust could become a key biosignature, helping us identify not just habitable planets, but potentially inhabited ones. It connects the microscopic world of mineralogy to the grand quest to find life elsewhere in the universe, showing how the humble dust grain is a key that can unlock mysteries on every scale, from the formation of planets to the potential prevalence of biology across the cosmos. Of course, the work done in pristine clean rooms and with powerful telescopes is only one half of this grand scientific endeavor. To truly make sense of the data extracted from a single speck of stardust, researchers rely on an entirely different kind of instrument, not one made of metal and glass, but of mathematics and code. This is the world of theoretical modeling and simulation, where astrophysicists build intricate digital universes inside supercomputers to replay the life cycle of cosmic dust. These are not simple animations. They are sophisticated virtual laboratories that encode the fundamental laws of physics, chemistry, and dynamics, allowing scientists to test their ideas about how dust forms, evolves, and is destroyed across billions of years and light years of space. A model might start with the basic ingredients, the composition of gas ejected from a specific type of star, the local temperature, and the density. Then the program runs, simulating the chaotic dance of atoms as they cool, collide, and eventually nucleate, forming the first seed of a dust grain. The model can then track that virtual grain as it journeys through a simulated interstellar cloud, predicting how its structure might be altered by shock waves, radiation, or collisions with other particles. The ultimate goal of this digital craftsmanship is to generate a specific set of predictions. What should the size distribution of grains from a supernova look like? What precise mix of graphite, silicates, and other minerals should we expect to find? Most importantly, what isotopic signatures should be locked into their crystalline structures? These predictions become a crucial roadmap for the scientists in the lab. When a cosmochemist measures an exotic isotopic ratio in a real pre-solar grain, they can turn to the modelers and ask, what kind of stellar environment produces this? The modelers can then run their simulations, adjusting the initial conditions, changing the mass of the star, the energy of the explosion, the mixing of the gases until the output of their virtual universe perfectly matches the real data from the grain. It's a powerful feedback loop where a microscopic, real-world discovery can validate or completely rewrite a theoretical framework that describes events of cataclysmic power. This constant dialogue between the infinitesimally small and the unimaginably large is what allows us to transform a raw measurement into a coherent story, a narrative of a grain's birth and journey. Furthermore, these models are indispensable for guiding our future exploration and making sense of what we see through our telescopes. Before we even point the James Webb Space Telescope at a distant protoplanetary disk, theorists will have run thousands of simulations predicting what its infrared spectrum should look like based on different compositions and distributions of dust. When the actual data comes back, astronomers can compare it to this library of simulated spectra to instantly narrow down the most likely scenarios, dramatically accelerating the process of discovery. Similarly, when planning a sample return mission to an asteroid, models help us choose the most promising target by simulating the formation and evolution of the solar system, predicting which bodies are most likely to be pristine time capsules rich in the ancient dust we seek. In this way, theoretical work doesn't just interpret the past, it actively shapes the future of research, ensuring that every expensive hour of telescope time and every daring robotic mission has the highest possible chance of success. It is the indispensable bridge that connects a raw observation to a profound understanding, continually refining and enriching our ever-evolving cosmic narrative. To understand the profound significance of these first dust grains, we have to rewind the cosmic clock to a time before any stars or galaxies even existed. The very early universe was a vastly different place, a hot, dense, nearly uniform soup of primordial gas composed almost entirely of hydrogen and helium. There were no heavy elements, no planets, and crucially, not a single speck of dust. This pristine environment, while simple, was also sterile. Without the complex chemistry that dust enables, the universe as we know it could not have evolved. The first stars to ignite in this darkness, known as Population 3 stars, were the true pioneers, and they were unlike anything that exists today. Theorized to be colossal behemoths, hundreds of times more massive than our Sun, they lived fast and died young, burning through their nuclear fuel in only a few million years before meeting cataclysmic ends in titanic supernova explosions. It is within these brief, violent lives and deaths that the story of dust truly begins. The nuclear furnaces in their cores were the first places in existence to forge heavier elements like carbon, oxygen, and silicon, the very raw materials of dust. When these stars exploded, they did more than just light up the cosmos. They seeded the void with the first heavy elements and, critically, the first generation of solid particles. In the expanding, cooling ejecta of these supernova, atoms of carbon and silicate could finally clump together, nucleating the very first microscopic grains of cosmic dust. This was a universe-altering event. That initial pollution of the primordial gas changed everything, providing the building blocks for future generations of stars and the catalyst for the complex cosmic evolution that followed. The challenge for modern astronomers is how to possibly observe this ancient, foundational era. We cannot see these first stars directly with any telescope we have or will ever build. They are too far away, too faint, and their light is stretched far into the infrared by the expansion of the universe. Instead, we have to become cosmic detectives, looking for the indirect clues they left behind. One of the most promising lines of evidence is to search for the dust they manufactured. We use powerful observatories like the Atacama Large Millimeter Array and the James Webb Space Telescope to peer back in time at the most distant, high-redshift galaxies. When we detect large amounts of dust in galaxies that existed when the universe was less than 1 billion years old, it presents a fascinating puzzle. The timescale is so incredibly short that only the first generation of massive population 3 stars could have produced the necessary heavy elements and dust that quickly. Finding dusty galaxies at such early cosmic epochs is therefore strong, indirect evidence for the existence of these first stars and their role as the universe's original industrial factories. It tells us they must have formed, lived, and died in a cosmological blink of an eye, rapidly transforming the simple early universe into a more complex, chemically rich environment. Another, even more subtle way to probe this dawn of creation is by studying the most ancient light we can detect, the cosmic microwave background. This faint glow is the remnant heat from the Big Bang, and it holds imprints of everything it encountered on its 13.8 billion-year journey to our telescopes. While most of the polarization patterns in this light are thought to be from the primordial universe itself, there is also a foreground contribution from much later, from dust within our own Milky Way galaxy. By creating exquisitely detailed maps of this galactic dust polarization, cosmologists can meticulously subtract its contaminating signal. This painstaking process is like listening for a whisper in a crowded room. You must first identify and remove all the other voices. But in doing so, they clean the data to get a clearer view of the primordial signal. This allows them to test theories about the very first moments of the universe, which in turn informs models about the initial density fluctuations that would eventually collapse to form the first stars. It's a deeply connected chain of evidence where understanding the dust in our galactic backyard is absolutely essential for correctly interpreting the faint echoes from the cosmic beginning, helping us piece together the conditions that allowed those first stellar giants to be born. This incredible chapter shows us that dust is not merely a byproduct of cosmic evolution. It was an essential catalyst that helped transition the universe from a simple, dark state into the complex, luminous, and structured cosmos we inhabit today. But the role of cosmic dust extends far beyond that of a passive museum artifact or a simple building block. It is also an incredibly active and creative force, a microscopic laboratory where the very chemistry of life can begin. In the deep, cold vacuum between the stars, the conditions seem utterly hostile to the formation of anything complex. Atoms and simple molecules are so spread out that the chance of two of them meeting, let alone reacting to form a more complex structure, is astronomically low. It would be like trying to get two specific people to bump into each other in an entirely empty continent. This is where the humble dust grain performs its most astonishing trick. Its solid surface provides a crucial meeting place, a tiny arena where the laws of chemistry are rewritten for the deep cold of space. Individual atoms like hydrogen, oxygen, and carbon drift through the void until they randomly stick to the frigid surface of a dust grain. There they are held in place, unable to bounce away, slowly migrating across the surface. This process, known as surface chemistry or grain surface catalysis, transforms the dust from a simple platform into an active participant, dramatically increasing the odds that these isolated ingredients will find each other and react. Imagine a lone oxygen atom adhered to a speck of silicate dust. A hydrogen atom, the most abundant element in the universe, eventually lands nearby and begins to skitter across the surface. When they meet, they can bond, forming a hydroxyl molecule. Another hydrogen atom arrives, and with a little energy, perhaps from the faint warmth of a distant star or the impact of a cosmic ray, it attaches to the hydroxyl, creating a full molecule of water right there on the grain's surface. This isn't a theoretical idea. It's the leading explanation for how water, so vital to life, became so abundant in the molecular clouds that eventually formed solar systems. The same process can build far more complex structures. Carbon atoms can link up with hydrogen to form long hydrocarbon chains. Nitrogen can join the mix, leading to the formation of precursor molecules to amino acids, and even the nucleobases that form the rungs of DNA's ladder. All of this intricate construction happens in the absolute cold, near absolute zero, where traditional, heat-driven chemistry would be impossible. The dust grain's surface provides the order and the opportunity for these reactions to proceed, acting as a universal catalyst that jump-starts molecular complexity across the galaxy. This changes our entire perspective on the abundance of prebiotic molecules, the chemical ingredients necessary for life. For a long time, scientists wondered how such fragile, complex compounds could be so widespread, detected by our telescopes in interstellar clouds and cometary comas. The answer appears to be that they are manufactured on site, on the surfaces of these countless trillions of dust grains, in a slow, cosmic-scale production line. This suggests that the universe is not just littered with the leftovers of stellar death, but is actively, continuously cooking the recipe for life itself in the dark between the stars. The dust is not merely a preserver of cosmic history, it is a factory for cosmic potential. It takes the simple elements forged in stars and begins assembling them into the more complex order that biology requires. This means that by the time a new star and its planets begin to coalesce from a cloud, that cloud is already preloaded with a rich supply of organic molecules, a veritable broth of prebiotic material. The dust grains that deliver this material to new worlds are therefore not just delivering raw elements, but partially assembled kits, giving planet-forming processes a significant and perhaps crucial head start. This profound activity positions cosmic dust as one of the most fundamental agents of chemical evolution in the universe, a silent, ubiquitous craftsman working in the darkness to create the conditions from which life can eventually emerge. This profound scientific discovery that we can hold the ashes of long-dead stars in our hands does something remarkable. It transcends the boundaries of the laboratory and reaches deep into the human spirit. It connects the cold, hard data of isotopic ratios to the warm, beating heart of our creativity and our deepest questions about existence. For centuries, poets and artists have used the stars as metaphors for dreams, for guidance, for the unattainable. But now we understand they are not just distant symbols, they are our literal ancestors, the revelation that the calcium in our bones, the iron in our blood, and the oxygen in our lungs were forged in the nuclear furnaces of stars that died billions of years ago, transforms a beautiful metaphor into a breathtaking physical reality. This idea of connectivity, that we are not just living on a planet but are an active, conscious part of the cosmos itself, has become a powerful muse. It inspires stunning visual art that depicts the swirling beauty of nebulas not as something far away, but as our own birthplace. It fuels science fiction narratives that explore our cosmic heritage, and it informs profound philosophical inquiries into what it truly means to be a citizen of the universe, bound by stardust to every other thing we see in the night sky. This cosmic perspective naturally cultivates a profound sense of humility, a quieting of the human ego that is both grounding and liberating. When we contemplate the journey of a single dust grain forged in a stellar explosion before Earth existed, drifting for eons through the void, surviving the chaotic formation of our solar system, and eventually becoming part of us, it becomes impossible to maintain the illusion that we are the isolated center of everything. Our planet is a tiny, fragile world orbiting an average star in a quiet corner of a galaxy that contains hundreds of billions of other stars, which is itself just one of perhaps 2 trillion galaxies in the observable universe. This isn't meant to make us feel insignificant, but rather to recontextualize our significance. We are not separate from the universe looking in. We are the universe itself, become conscious and able to reflect upon its own origins. This shift in viewpoint from a geocentric to a cosmocentric existence is one of the most important philosophical gifts of modern astronomy. It encourages us to see our personal worries, our tribal conflicts, and even our grandest human achievements within a much larger, more ancient, and more wondrous narrative. This blending of scientific inquiry with existential reflection creates a unique and powerful way of engaging with the world. It allows us to appreciate the cosmos not just as a collection of physical objects to be catalogued, but as a story in which we are both characters and readers. Every time we look up at the stars, we are not just seeing points of light, we are looking at the homes of our elemental origins. A sunset is not just a daily event, it is a demonstration of interstellar dust scattering light in our atmosphere, a direct interaction with the very material that built our world. This deeper appreciation fosters a sense of stewardship and wonder. It compels us to protect our fragile planet, the only home we have ever known, precisely because we understand how rare and precious the long chain of cosmic events that led to its formation truly is. It transforms our relationship with the universe from one of passive observation to one of active participation and reverence, inviting us to continue the work of the stars by using our own consciousness to create, to understand, and to find meaning in the grand, dusty tapestry of existence. Perhaps one of the most beautiful aspects of this entire field is how it effortlessly bridges the gap between the profoundly complex and the wonderfully accessible, inviting everyone to share in the wonder of discovery. This isn't research locked away in an ivory tower. Cosmic dust has a unique, democratic quality that allows it to become a powerful tool for education and public engagement, sparking curiosity in people of all ages and backgrounds. Museums around the world have tapped into this universal fascination by creating stunning exhibits centered on micrometeorites. Imagine walking through a natural history museum and coming face to face with a display that lets you peer through a microscope at genuine specks of stardust that have fallen to Earth. These aren't replicas or models, they are the real microscopic articles often collected from rooftops or Antarctic ice. For a child, this can be a transformative moment. The realization that the universe is not some distant, abstract concept, but a tangible presence, something that literally rains down upon us and can be held, in a sense, in their own hand. It makes the cosmos personal and immediate in a way that a photograph of a distant galaxy, for all its beauty, sometimes cannot. This spirit of inclusion extends far beyond the museum wall and directly into people's homes through the growing world of citizen science. Projects like NASA's Stardust at Home initiative have brilliantly demonstrated that you don't need a PhD to contribute to real, cutting-edge astrophysics. In this project, thousands of volunteers from all walks of life spent hours poring over digital images of the aerogel collector from the Stardust mission, searching for the telltale minuscule tracks left by impacting interstellar dust particles. It was a monumental task, a proverbial search for a needle in a haystack, but one that human eyes and pattern recognition are uniquely suited for. These dedicated volunteers, these cosmic sleuths, were ultimately responsible for identifying several of the most promising candidate particles for further study. They weren't just passive observers, they were active participants in the process of discovery, co-authors on scientific papers, and integral members of the research team. This model empowers people, giving them a genuine stake in the outcome and fostering a deeper connection to the scientific endeavor, transforming abstract appreciation into tangible contribution. The narrative power of cosmic dust also makes it a perfect subject for documentaries and other forms of science media. Filmmakers can tell a compelling story that follows the journey of a dust grain across billions of years, weaving together spectacular visual effects of stellar explosions with intimate footage of scientists working at their benches in clean rooms. These stories humanize science, showing the passion, the perseverance, and the occasional frustration that drives researchers forward. They translate complex isotopic data into a relatable saga of exploration, making the audience care about the fate of a particle they can't even see. This kind of storytelling is essential. It doesn't dumb down the science but rather illuminates its human context, showing the curiosity and collaboration that are the true engines of progress. By sharing these discoveries in such an engaging format, scientists and communicators do more than just convey information. They plant seeds of inspiration. A teenager watching such a documentary might be inspired to pursue a career in astronomy. A teacher might develop a new lesson plan about the solar system, and a retiree might find a new passion in learning about the universe. This outreach ensures that the story doesn't end with a published paper but continues to ripple outward, inspiring the next generation of explorers, critical thinkers, and lifelong learners who will carry the torch of curiosity forward. This accelerating pace of cosmic collection, while opening incredible scientific doors, also forces us to confront a new set of complex ethical questions that extend far beyond our own planet. We are no longer passive observers of the cosmos. We are now active collectors, and with that role comes a profound responsibility. The very act of reaching out and taking a sample from an asteroid, a comet, or even the pristine environment of Mars inherently changes that environment. A primary concern is the risk of forward contamination, the potential for us to inadvertently pollute these other worlds with our own earthly biology. Even the most sterile spacecraft and cleanroom protocols cannot guarantee absolute biological purity. A single, resilient Earth microbe hitching a ride on a lander or a sampler arm could, in theory, survive and proliferate in a new environment, irrevocably altering it and forever destroying our ability to study it in its natural, untainted state. This isn't just about protecting alien ecosystems that may or may not exist. It's about protecting the integrity of these cosmic archives themselves. If we were to find complex organic molecules on Mars, for instance, the first question would be, are these truly Martian or are they something we brought with us? Our quest for knowledge must not become the very thing that corrupts the evidence we seek. This leads directly to weighty questions of ownership and stewardship. Who exactly has the right to collect and possess these materials? A sample returned from an asteroid represents a piece of our solar system's primordial building blocks, a relic that belongs to no single nation but to the shared heritage of humanity. The current framework for navigating this celestial real estate is a patchwork of international agreements, most notably the Outer Space Treaty of 1967, which forms the bedrock of international space law. This treaty explicitly states that celestial bodies are not subject to national appropriation by claim of sovereignty, meaning no country can plant a flag on an asteroid and declare it their own. However, the treaty is notably silent on the specifics of resource extraction and sample ownership, leaving a gray area that nations and now private companies are beginning to explore. More recent discussions, particularly around the Artemis Accords, are attempting to build upon this foundation, proposing concepts like safety zones around exploration sites and promoting the idea that extracted resources can be owned by the entity that collected them, even if the celestial body itself cannot be claimed. The goal is to foster a spirit of cooperation and responsible exploration, ensuring that the scientific and potential economic benefits of cosmic resources are managed fairly and do not lead to conflict or the irresponsible exploitation of our shared solar system. Ultimately, these ethical considerations are about adopting a long-term perspective, one that views our solar system not as a frontier to be plundered but as a library to be studied with care. Every mission we send out, every sample we retrieve, sets a precedent for future generations of exploration. If we approach these pristine environments with a short-sighted, gold rush mentality, we risk damaging or destroying unique scientific records that have been preserved for billions of years, records we may not even fully understand how to read yet. The samples we collect today are not just for us, they are for the scientists of the future who will have tools and techniques we cannot yet imagine, capable of extracting even more detailed stories from these ancient messengers. Our ethical duty, therefore, is to act as conscientious stewards. This means implementing and strictly adhering to planetary protection protocols, engaging in transparent international collaboration to share both the samples and the knowledge they yield, and always prioritizing the preservation of these irreplaceable cosmic archives for the benefit of all humankind. It is a delicate balance between our insatiable curiosity to understand the universe and our profound responsibility to protect it, ensuring that our first footsteps into the wider cosmos are taken with thoughtfulness, respect, and a commitment to preserving the memory of creation for all who follow. This incredible detective work, piecing together the history of a galaxy from microscopic specks, is a feat that no single scientist could ever accomplish alone. It demands a symphony of expertise, a true meeting of the minds from fields that might seem worlds apart. An astronomer might first identify a distant, dusty nebula where new stars are forming, using a powerful telescope to determine its composition from the light it emits. But to truly understand what that dust is made of and what it means, they need to partner with a chemist. That chemist can then analyze the actual samples we collect, using mass spectrometers to break down the grains into their atomic components, revealing the isotopic fingerprints that point back to a specific type of stellar explosion. Yet the story doesn't end with chemistry. A geologist's perspective is absolutely vital because they are the experts in how solid materials form, change, and endure over time. They can look at the crystal structure of a dust grain under an electron microscope and interpret its history, whether it was forged in a sudden, violent shockwave or slowly annealed in the gentle warmth of a stellar wind, reading the thermal history of the grain like the rings of a tree. Perhaps most surprisingly, the circle of collaboration now extends to biologists. The discovery that cosmic dust can carry complex organic molecules forces us to ask a profound biological question. Could these interstellar ingredients have played a role in sparking life on Earth or elsewhere? A biologist brings a completely different set of tools and questions to the table. They can design experiments to test how these extraterrestrial organic compounds behave in watery environments that mimic early Earth, or investigate whether they can catalyze the kinds of reactions that lead to self-replicating molecules. They can assess the biological potential of what the dust delivers, asking whether the universe is not just physically, but also biologically fertile. This synergy is transformative. A biologist might never look through a telescope, and an astronomer might never pipette a solution in a lab. But by sharing their findings, they create a feedback loop that accelerates discovery for everyone. The astronomer's observation guides the chemist's analysis, which informs the geologist's interpretation, which then fuels the biologist's experiment. Each specialist provides a unique piece of the puzzle, and it is only when these pieces are connected that the full, breathtaking picture emerges. This collaborative model is a powerful testament to how modern science actually works. The era of the lone genius toiling in isolation is long gone. The biggest questions about our universe demand a team-based approach. A physicist might develop a complex model predicting how dust grains should align in a magnetic field, but it takes an engineer to build the sensitive polarizing detector on a satellite that can test that prediction. A computer scientist is needed to write the algorithms that can sift through terabytes of telescope data to find the faint signature of a dusty disk around a distant star. This interconnectedness shows that the boundaries between scientific disciplines are not walls but bridges. The quest to understand a speck of dust pulls down these artificial barriers, creating a shared language and a common goal. It proves that the deepest cosmic mysteries cannot be solved by looking through a single lens, but require us to combine every tool at our disposal, from the infinite reach of astronomy to the microscopic precision of biology, weaving together every thread of knowledge to unravel the story of our Stardust origins. Now, let's expand our view beyond our own solar backyard and consider the incredible discoveries being made around other stars. When we point our most powerful telescopes at distant exoplanetary systems, we're often not seeing the planets themselves directly. Instead, we're seeing their dusty fingerprints. These aren't the sparse, primordial clouds of a forming system, but the telltale signs of mature systems, the leftover debris and collisionally generated dust that paints a vivid picture of dynamic activity. We observe vast, swirling debris disks, often reminiscent of our own Kuiper belt but on a much grander scale. These rings and arcs of dust are the aftermath of planet formation, the leftover building blocks that never coalesced into larger worlds, or the shattered remains of countless asteroid collisions happening in real time. The very presence and structure of this dust act as a powerful diagnostic tool. A smooth, continuous disk might suggest a relatively calm system, whereas a disk with sharp edges, gaps, or warps almost certainly signals the gravitational presence of unseen planets. their orbits clearing paths and shepherding the dust into specific patterns, much like Saturn's moons sculpt its rings. The composition of this exoplanetary dust, which we can often determine by analyzing the specific wavelengths of light it emits or absorbs, opens an entirely new window into these alien systems. Using instruments like the James Webb Space Telescope, astronomers can detect the infrared signatures of specific minerals, silicates, carbon compounds, water ice within dust clouds light years away. Finding a debris disk rich in water ice crystals, for instance, would strongly suggest that the system has a well-defined snow line similar to our own, a boundary beyond which volatile ices can survive. This isn't just a trivial detail, it directly informs the types of planets that could form there. A system with carbon-rich dust might be more likely to form planets with graphite or diamond in their crusts, while a system dominated by silicate dust would be a factory for rocky, Earth-like worlds. The dynamics of the dust are equally revealing. By studying how the dust moves and evolves over time, we can infer the presence of asteroid belts and even spot the chaotic collisions that generate fresh clouds of debris, events that might be seeding the inner planets with water and organic materials, just as we suspect happened in our own early solar system. This ability to compare and contrast is where the true power of this research lies. Our own solar system is a single, detailed data point. Is it a typical example of how planetary systems form and evolve, or is it a cosmic oddity? By studying the dust in hundreds of other systems, we can finally begin to answer that question. We see systems that look like youthful versions of our own, with massive, bright debris disks indicative of frequent collisions. We see older, quieter systems where the dust has mostly settled, perhaps resembling our solar system in its current, middle-aged state. And we see utterly alien architectures, disks tilted at extreme angles, systems with multiple overlapping belts, or stars surrounded by clouds of dust that could only have been created by a recent, catastrophic collision between planet-sized bodies. This comparative planetology allows us to gauge the universality of the processes we understand. It helps us determine which aspects of our solar system's story are common chapters in a universal playbook and which are unique plot twists. Ultimately, this all ties back to the grand, haunting question of life elsewhere. The composition and distribution of dust in an exoplanetary system is a powerful proxy for its potential habitability. A system with a rich reservoir of water ice dust in its outer regions increases the odds that any terrestrial planets in the habitable zone could have been water delivered via comet impacts. A dynamic asteroid belt, evidenced by persistent warm dust close to the star, suggests an ongoing delivery system of organic rich material to inner planets, potentially continuously seeding them with the building blocks of life. Conversely, a system with little to no dust, or dust with a composition devoid of key volatiles, might be a sterile desert, lacking the essential ingredients for biology as we know it. So, by studying this faint, swirling dust, we are not just reading the history of these distant systems, we are making an educated assessment of their biological potential. We are beginning to statistically estimate just how many worlds out there might have been built from similar materials, shaped by similar processes, and blessed with the same cosmic deliveries that set the stage for life to emerge here on Earth. While we often look to the heavens or to meteorites for our samples of cosmic dust, some of the most patient and meticulous detectives in this field are looking much closer to home, literally beneath our feet and deep within the ice. These researchers are engaged in a different kind of treasure hunt, sifting through the layered archives of our own planet to find microscopic messages from space that fell to Earth not years or decades ago, but millions of years in the past. They are searching for ancient cosmic dust that has been preserved and sequestered within the slow-growing geological records of our world, in the sediments of ancient seafloors, in the accumulated layers of Antarctic ice cores, and even within the rock formations on land. This approach adds an entirely new and profoundly important dimension to the cosmic dust narrative, because it gives us something we can't get from any other source: a timeline. By finding these particles in dated layers of Earth's crust, we can pin their arrival to a specific moment in our planet's deep history, turning a single speck into a data point in a vast chronological record of our solar system's interaction with the wider galaxy. The process of finding this ancient dust is a monumental exercise in patience and precision. Imagine a team of scientists on an ice sheet in Antarctica, drilling down over 2 miles to extract a core of ice that has been accumulating for nearly 1,000,000 years. Each layer in that core represents a specific year, much like a tree ring, preserving a sample of the Earth's atmosphere from that time, including any extraterrestrial dust that settled out of it. Back in the laboratory, they will meticulously melt small sections of this ice and filter the water through incredibly fine filters, searching for the tiny, magnetic, or uniquely shaped particles that stand out from the terrestrial background. On the other end of the spectrum, paleoceanographers will take core samples from the deep sea floor, where sediment has been accumulating at a rate of just a few millimeters every 1,000 years. In these dark, anoxic layers, free from the churning of currents and life, cosmic dust can lie undisturbed for eons. The challenge is that in both cases, the extraterrestrial material is incredibly diluted, making up perhaps only a few parts per million of the entire sample. Isolating it requires a combination of physical separation using magnets to attract iron-rich particles and sophisticated chemical treatments that dissolve away the earthly material, leaving behind the resilient cosmic grains. So what incredible stories can this ancient terrestrial dust tell us? One of the most dramatic involves nearby stellar explosions. If a supernova were to occur within a few hundred light-years of our solar system, the models predict that it would shower the Earth with a specific pulse of radioactive isotopes like iron-60, which is not naturally produced on our planet. This isotope has a half-life of 2.6 million years, so it wouldn't survive from the formation of the solar system, but it would be detectable if it arrived relatively recently in geological terms. And that's exactly what researchers have found. By analyzing deep-sea sediment cores and manganese crusts that have grown over millions of years, teams have identified distinct layers enriched with iron-60. These layers act like geological stopwatches, precisely dating these interstellar events. The evidence points to a series of supernovae that occurred around 2 to 3 million years ago, close enough that our early human ancestors might have seen the brilliant new star light up the sky, and potentially even felt the effects of the increased cosmic radiation reaching the Earth's surface, which some scientists speculate could have influenced our planet's climate and cloud cover. Beyond these catastrophic stellar deaths, this ancient dust record can reveal more subtle, long-term rhythms of our solar system's journey through the galaxy. As our Sun orbits the center of the Milky Way, it doesn't travel a perfectly smooth path. It bounces slightly up and down through the galactic plane, and it also moves through spiral arms and regions of differing dust density. These grand galactic motions might subtly influence the flux of interstellar dust entering our solar system. By measuring the rate of cosmic dust accumulation in Earth's sediments over millions of years, scientists can potentially detect these long-period cycles. A gradual increase in certain types of pre-solar grains in the geologic record could indicate a time when our solar system was plowing through a particularly dense cloud of interstellar material, a cloud that might have been ejected from a stellar nursery or a supernova remnant millions of years earlier. This turns the Earth itself into a giant cosmic dust collector, its geological layers recording a million-year history of our local interstellar environment, a history we can now begin to read by studying the smallest particles trapped within it. This incredible work connects the grandest scales of galactic motion to the most microscopic of samples, all found right here at home, weaving together the story of the soil and the sky into a single, continuous tapestry of cosmic evolution. Now, as we venture into one of the most profound mysteries of modern cosmology, we find ourselves at a fascinating intersection where the study of the very small and the very large collide in a surprising way. While cosmic dust is made of the ordinary atoms we're all familiar with, the very act of trying to understand it has become deeply entangled with the hunt for something entirely different and utterly mysterious: dark matter. This invisible substance makes up about 85% of all the matter in the universe, yet it refuses to interact with light, revealing its presence only through its immense gravitational pull on galaxies. The quest to directly detect a single particle of dark matter here on Earth is one of the most challenging experiments ever conceived, and it turns out that the humble speck of interstellar dust has become an unexpected and crucial character in this cosmic detective story. The challenge is that the signal scientists are desperately searching for in their ultra-sensitive detectors deep underground are incredibly faint and rare. They are looking for the tiniest possible vibration or flash of light that would indicate a dark matter particle has finally bumped into an atom of ordinary matter. The problem is that other things can cause similar little bumps and flashes, creating a background of false signals that can perfectly mimic the signature of dark matter. And one of the most pervasive sources of this background noise is, you guessed it, cosmic dust. This might seem counterintuitive at first. How can a microscopic grain of dust possibly interfere with a state-of-the-art physics experiment? The connection is not the dust itself, but what it can carry. Some cosmic dust grains, during their long journey through space, can become ionized, meaning they pick up a slight electric charge from exposure to cosmic radiation. This charged microscopic particle, when it eventually falls to Earth and finds its way into an exquisitely sensitive detector, can produce a signal that looks, for all intents and purposes, identical to the one physicists would expect from a dark matter particle interaction. It's a case of cosmic mistaken identity, where a known piece of interstellar debris can perfectly impersonate the unknown substance we're trying to find. This means that the teams operating these detectors, housed in places like deep mines or under mountains to shield them from other types of interference, must become experts not just in particle physics, but also in micrometeoritics. They have to develop incredibly sophisticated methods to identify and subtract this dust-induced background noise from their data. They meticulously analyze the precise timing, the energy profile, and the pattern of each signal, looking for the subtle telltale signs that betray its earthly or interstellar origin rather than a truly exotic one. This necessity has forged an unlikely but powerful alliance between cosmologists studying the largest structures in the universe and scientists who specialize in the most minute analysis of dust grains. To confidently claim a discovery of dark matter, researchers must first achieve a near-complete understanding of every other possible explanation, and that requires a deep knowledge of the composition, magnetism, and behavior of cosmic dust. In a very real sense, the study of the known, the well-understood physics of dust is what allows us to sharpen our search for the unknown. By building better models of how dust behaves and how it can contaminate experiments, physicists can fine-tune their detectors, improve their shielding, and develop more advanced filtering algorithms. This process of elimination, of systematically accounting for every possible mundane explanation, is how science often progresses at its very frontiers. The search for dark matter is therefore not just a story about building bigger and more sensitive machines. It is also a story about achieving a profound mastery over the smallest details of our own cosmic environment. It illustrates a beautiful principle of scientific inquiry, that the path to unlocking the universe's deepest secrets often requires us to first fully understand the ordinary world right in front of us, proving that even the most common dust can hold lessons that illuminate the nature of the elusive dark. And yet, for all the profound data these microscopic particles provide, their impact is not confined to the sterile environment of a laboratory or the complex equations of a theoretical model. They possess a second, equally powerful language, one of pure, breathtaking visual splendor that speaks directly to our sense of wonder. When we gaze upon the iconic pillars of creation captured by the Hubble Space Telescope, we are not just looking at a scientific object, we are witnessing a masterpiece on a cosmic canvas. Those towering, ethereal structures are not solid rock but colossal clouds of gas and dust, brilliantly illuminated and sculpted by the fierce radiation of nearby newborn stars. The delicate tendrils, the rich textures, the deep shadows, this is the artistry of cosmic dust, playing with light on a scale so vast it defies human comprehension. It is a landscape of creation and destruction, where the very material that blots out starlight also reflects and scatters it into the magnificent nebulae that have become some of the most celebrated images in human history. This beauty is not an accidental byproduct. It is a fundamental characteristic of the physics at work, a visual symphony composed by the interplay of matter and energy. This artistic dimension of the cosmos serves a crucial purpose beyond mere decoration. It forges a powerful emotional bridge between the cold, hard facts of astrophysics and the innate human desire for wonder and meaning. A person might not fully grasp the nucleosynthesis processes that forge the elements within a nebula, but they can instantly feel a sense of awe, humility, and profound connection when confronted with its image. This emotional response is a gateway to curiosity. The beauty draws us in, making the underlying science more accessible and infinitely more compelling. It transforms the universe from an abstract concept studied by others into a tangible, magnificent reality that we are a part of. We are not just learning about the cosmos, we are being invited to appreciate it, to feel a sense of kinship with its grandeur. This blend of the rational and the sublime is perhaps science's greatest strength, reminding us that the pursuit of knowledge does not diminish wonder but amplifies it, revealing a universe that is both intelligible and utterly magnificent. This fusion of art and science finds its most potent expression in the work of the astrophotographers and imaging specialists who translate raw telescope data into the breathtaking visuals we share. Their process is itself a form of meticulous interpretation, a collaboration between human creativity and cosmic reality. They must assign colors to represent different elements: hydrogen, oxygen, sulfur, emitting light at wavelengths invisible to our eyes, not to falsify the image, but to reveal its hidden structure and composition. The resulting picture is both a scientifically accurate map and an artistic composition, designed to convey the drama, the scale, and the intricate beauty of the celestial landscape. In this way, a single image of a dust-filled nebula becomes a universal language, understood by a scientist, an artist, and a child alike, each taking away something different but equally valuable. It democratizes the cosmos, making its wonders available to everyone with an internet connection and a sense of curiosity, proving that you don't need a PhD to develop a deep, personal relationship with the universe. This shared appreciation for cosmic beauty fosters a collective sense of stewardship and inspiration, uniting us in awe under the same starry sky and fueling the imagination that drives all scientific discovery forward. Perhaps one of the most inspiring aspects of this entire cosmic quest is how the incredibly specialized tools developed to study Stardust don't just help us understand the universe, they often circle back to profoundly improve life here on Earth. The extreme challenges of handling and analyzing these microscopic time capsules have forced scientists and engineers to become pioneers, inventing new technologies and refining existing ones to a razor's edge. These innovations, born in the sterile silence of clean rooms and the high-stakes environment of space missions, frequently find powerful and sometimes unexpected second lives in fields as diverse as medicine, manufacturing, and protecting our environment. This beautiful cycle of knowledge transfer demonstrates that investing in pure, curiosity-driven space science doesn't just expand our cosmic horizons. It actively drives innovation that ripples through our entire society, creating tangible benefits that touch our daily lives. Consider the incredible lengths required to prevent contamination of a cosmic dust sample. The entire process, from designing a spacecraft sampler to handling a grain in the lab, demands an almost obsessive level of cleanliness that makes a hospital operating room look chaotic by comparison. To achieve this, researchers developed and perfected ultra-stringent clean room protocols, advanced air filtration systems that remove particles down to a nanometer in size, and specialized non-shedding garments. These rigorous contamination control standards have been eagerly adopted by the semiconductor industry, where a single speck of dust can ruin an entire silicon wafer, costing millions of dollars. The techniques for handling pristine cosmic materials directly influence the manufacturing processes that produce the ever smaller, more powerful microchips at the heart of our phones, computers, and medical devices. This transfer of knowledge from astromaterials labs to microchip fabrication plants is a perfect example of how solving a problem for fundamental science can yield massive technological and economic dividends. The story continues with the instruments themselves. To even see a pre-solar grain, let alone analyze its atomic structure, requires microscopes of staggering power and precision. The constant drive in cosmochemistry to see finer details and measure more precise elemental compositions has pushed the development of electron microscopes and secondary ion mass spectrometers to incredible new heights. These are not off-the-shelf instruments. They are often one-of-a-kind machines, custom-built and relentlessly refined in a kind of feedback loop with the cosmic dust they are designed to study. The high-resolution imaging capabilities of these advanced microscopes are now indispensable in medical research, allowing biologists to visualize viruses, proteins, and cellular structures in breathtaking detail, which is crucial for developing new drugs and understanding diseases at a fundamental level. Similarly, the ultrasensitive mass spectrometers, honed to detect the faintest isotopic whispers from a stardust grain, are now used in environmental labs to trace the source of pollutants in water, supplies with pinpoint accuracy, or to detect minuscule, early-stage biomarkers for diseases like cancer in blood samples, enabling earlier and more effective treatment. This technological spin-off effect even extends to the materials used in the collection process itself. NASA's Stardust mission needed a substance that could gently capture hypervelocity particles without destroying them, leading to the development and use of aerogel, one of the lightest solid materials ever created. This incredible substance, with its ethereal, ghostly appearance, has since found a wide array of applications. Its exceptional insulating properties make it ideal for everything from high-performance building insulation to designing next-generation energy-efficient refrigerators. Chemical engineers use it as a fantastic catalyst support due to its vast surface area, and it's even being explored for use in advanced drug delivery systems within the human body. The quest to catch Stardust quite literally gave us a new material with the potential to reshape entire industries. Ultimately, this ongoing process is a powerful reminder that the lines between different fields of research are often beautifully blurred. A breakthrough in our understanding of a supernova's dust output can, through a long and unpredictable chain of innovation, lead to a new medical diagnostic tool or a better way to monitor our planet's health. It proves that funding space exploration and fundamental science is never just about looking outward. It is also a deep investment in our own future, fostering a culture of innovation that solves practical problems and improves the human condition. The technologies forged in the fire of cosmic curiosity become gifts to the whole of society, demonstrating that the journey to grasp the stars invariably leaves us with a better, smarter, and more capable world right here on the ground. Despite its dramatic origins in stellar explosions and its profound scientific importance, cosmic dust is often misunderstood, shrouded in a cloud of common myths that can obscure its true nature. One of the most persistent misconceptions is the idea that this material is somehow dangerous or toxic to life on Earth. This notion likely springs from our everyday experience with dust, which we associate with allergens, pollutants, and the need for constant cleaning. But the reality of extraterrestrial dust is vastly different. While tons of it do indeed rain down on our planet every single year, it is almost entirely harmless. The particles are so incredibly small and so widely dispersed as they settle through the atmosphere that they pose no risk to human health. In fact, you have almost certainly inhaled specks of stardust without ever knowing it. This material is a natural part of our environment, a gentle, constant cosmic precipitation that has been falling for billions of years, long before humans ever walked the planet. Another widespread belief is that cosmic dust is vanishingly rare, a substance so exotic that only the most powerful scientific instruments could ever hope to find it. This myth makes the study of it seem like an impossibly esoteric field, disconnected from our everyday reality, but the truth is far more democratic and fascinating. While individual pre-solar grains are rare and require sophisticated methods to isolate, interplanetary dust is remarkably common. You don't need a spacecraft or a massive telescope to find it. You can collect it from the gutters of your own roof. Amateur scientists and dedicated enthusiasts around the world do exactly that, using magnets to sift through rainwater runoff to find tiny, magnetic micrometeorites. These particles are the melted, spherical remains of larger dust grains that have vaporized upon entering our atmosphere at high speed, and they are a tangible, collectible link to the wider solar system. This accessibility transforms cosmic dust from an abstract concept into something personal and immediate, a piece of space that anyone can hold in their hand. Perhaps the most significant myth to dispel is the idea that this entire field of study is purely theoretical, with no real connection to our understanding of the universe or ourselves. Some might wonder how studying something so small could possibly tell us anything about something as vast as a galaxy. This misconception undervalues the incredible power of these microscopic archives. Each grain is a data point, a physical sample that carries quantifiable information. The isotopic ratios within a single speck are not a matter of speculation. They are hard, empirical evidence of the specific stellar environment that created it. This is not guesswork, it is forensic science on a cosmic scale. By dispelling these myths, we open up a more accurate and far more exciting public conversation. We can move beyond fear and abstraction to a place of engagement and wonder, where people understand that they are literally connected to the cosmos through the dust that falls around them. and that the quest to understand it is one of the most tangible and rewarding adventures in all of modern science. Behind every tiny speck of interstellar dust that reveals a universe of secrets, there are scientists whose curiosity and dedication have turned a seemingly esoteric pursuit into a profound human adventure. These are not just names on research papers, they are modern-day explorers embarking on missions that demand equal parts intellectual brilliance and sheer physical perseverance. Consider the daring collectors who board specialized high-altitude aircraft like NASA Ur-2, which flies at the very edge of our atmosphere to sweep the stratosphere for pristine particles. Strapped into a cockpit and soaring for hours, these researchers are essentially astronauts of the upper atmosphere, enduring thin air and extreme cold to deploy collectors that act as cosmic flypaper. Their work is a delicate ballet of precision and patience, knowing that a single moment of contamination could ruin months of preparation, all for the chance to capture a few precious micrograms of material that have journeyed across the solar system. Then there are the laboratory alchemists, the scientists who receive these priceless samples. Their stage is not the vastness of the sky, but the sterile, hushed environment of a clean room, where they don full body bunny suits to avoid introducing a single human cell into their work. Their tools are not wrenches and flight controls, but microscopic needles, nanomanipulators, and instruments of astonishing sensitivity. They might spend an entire day, or even a week, carefully maneuvering a single dust grain, smaller than the period at the end of this sentence, from one chamber of a microscope to another. The pressure is immense. One wrong move, one static shock, one barely perceptible tremor, and a unique billion-year-old record of a stellar explosion could be lost forever. Theirs is a world of intense focus, where the grand narrative of cosmic evolution is painstakingly reconstructed one atomic ratio at a time. What unites these diverse individuals is a shared, almost palpable sense of wonder and a deep-seated curiosity about our place in the universe. For every researcher, there is a story, a moment that cemented their path. For some, it was the first time they looked through a microscope and saw the intricate crystal structure of a grain that predated our sun, a tangible piece of another star. For others, it was the thrill of being part of a team that identified a new type of mineral never before seen in nature, all within a particle smaller than a bacterium. These moments of discovery are not just professional victories, they are profoundly personal, the reward for years of meticulous, often frustrating work. They speak to a powerful drive not for fame or recognition, but for the simple, exhilarating act of uncovering a truth that has been waiting in the darkness of space for billions of years, just hoping for someone to come along and read it. This endeavor is also a powerful testament to the spirit of collaboration. A cosmochemist in Chicago might spend months analyzing a grain, only to send it to a colleague in Japan for a different type of analysis using a unique instrument. The data then goes to a theoretician in Germany who runs it through sophisticated models of stellar nucleosynthesis. There is no single hero in this story. Progress is a chorus of voices, each adding a unique piece to the puzzle. This global conversation, conducted over email, video calls, and at international conferences, highlights how understanding our cosmic origins is a fundamentally human enterprise, built on trust, shared excitement, and the collective belief that the universe has a story to tell, if only we are patient and clever enough to listen. Their work, often conducted in anonymity, is a beautiful reminder that the greatest explorations are not just about going to new places, but about seeing the familiar world and our own existence within it in an entirely new light. Cosmic dust is so much more than the simple debris it might appear to be. These microscopic particles are the universe's most resilient and patient historians. silent witnesses to the grandest events across billions of years, preserving the very memory of creation within their intricate atomic structures. They carry within them the stories of stellar furnaces, the chaotic beauty of supernova, and the gentle, slow exhale of dying red giants, from the formation of the very first stars that ever ignited to the delivery of the fundamental building blocks of life itself. These interstellar archives offer us a tangible, physical connection to our deepest origins and perhaps even to our cosmic destiny. They are a bridge across time and space, allowing us to hold a piece of a star that died long before our sun was even born. As our technology continues to advance at a breathtaking pace, our ability to decode these ancient messages grows ever more sophisticated. New generations of space telescopes, more sensitive laboratory instruments, and daring sample return missions to asteroids and comets promise to unveil secrets we can currently only dream of. We are on the cusp of not just reading these cosmic archives, but of truly understanding the full narrative they contain, a story that is ultimately our own. This ongoing quest deepens our connection to the cosmos in the most profound way, transforming us from passive observers into active participants in a universe that is both knowable and wondrously mysterious. So the next time you find yourself in a quiet room watching dust motes dancing in a sunbeam, take a moment to really consider them. That gentle, ordinary light is illuminating something extraordinary. You are not just looking at household lint, you are glimpsing a fragment of the universe's epic story, a story of cataclysm and creation, of journeys across light years, and of our own stardust beginnings. It's a beautiful reminder that the cosmos is not some distant, unreachable place. It is all around us and it is a part of us. We'd love to hear what fascinates you most about this incredible cosmic connection. Share your thoughts and your own sense of wonder in the comments below. And if you've enjoyed this journey through the archives of creation, don't forget to subscribe and hit the notification bell so you can join us for our next exploration into the great mysteries